Power versus speed. There's always been a tug of war between these two within the technology space. And when it comes to AI, there's no different. I call it the battle of milliwatts versus milliseconds, right? And once you grasp this concept, you'll start to see the tech world in a whole new light. When it comes to speed, and when it comes to speed in AI, speed isn't just a nice to have. It's often a matter of survival. So imagine a self-driving car's AI needing to identify a pedestrian. Every millisecond counts. So this is what we call latency, which is really the delay between an input and an output. And in critical AI applications, low latency can literally be the difference between life and death. Now, traditional computer processors known as CPUs, they use sequential thinking, let's call it that way. They handle one calculation at a time. While versatile, this approach is a little bit, simply too slow for modern AI's demanding needs. And so the game changed some years ago when they brought in GPUs, graphical processing units. Now those really came about because of the whole gaming, but these are designed to perform thousands of calculations simultaneously, making them incredibly effective for training large AI models and handling a high volume of AI tasks known as inference. So this is why GPUs still dominate in many large-scale AI operations. However, for very specific tasks in AI, there's another type of chip called an FPGA, a field programmable gate array, right, which can actually surpass GPUs in inference speed. Think of FPGAs as a custom-built highway designed specifically for your AI model. There are no traffic jams or unnecessary detours, just pure, tailored, parallel processing that's incredibly efficient for its particular workload. Now then, there's the other part, the reality of power and power consumption, right? At the end of the day, what's the point of speed if your device runs out of juice in minutes? Power efficiency is what truly distinguishes a cool lab demo from a practical, real-world product. So high-end GPUs used for AI training can consume over 300 watts of power. Now, 300 watts of power, that's comparable to running multiple microwaves. Even GPUs used for inference can consume 50 to 150 watts. So while this is fine for data centers with specialized cooling systems, it's completely impractical for devices like drones that need to operate for hours on battery. And this is where another type of chip, the ASICs, come in. ASICs are application-specific integrated circuits. Again, they've been around for a while too. This is where they truly shine. So think about Google's TPUs or NVIDIA's TPUs. ASICs are specifically designed for their AI workloads. They perform incredibly well while using a fraction of the power of a general-purpose GPU. FPGAs offer a compelling middle ground, right? They're reconfigurable like software, but operate with the efficiency of hardware. When optimized for specific AI tasks, FPGAs can be up to 10 times more power efficient than GPUs. So when it comes to architecture, AI architecture, smart engineers, they're not just looking at the fastest chip, right? Instead, they design AI systems with real-world limitations and constraints in mind. So let's talk, for example, I'll give you an example, cloud AI training. Here, power is less of a concern than raw processing power. Right? So tracking or so stacking GPUs is preferred. And there's cloud inference at scale, which requires a balance of speed versus efficiencies. So GPUs handle large, complex models, while you can use ASICs to take care of more specific tasks. And then there's edge devices like smartphones or drones, where battery life is paramount. So custom ASICs and specialized FPGAs are the go-to choice for these particular scenarios. And then we have the real-time systems, where you want predictable, low latency. In these cases, that's much more important than the maximum throughput. So in this case, you're looking at well-designed FPGAs. This is where they excel the most. So the future of AI isn't about one chip conquering all. It's about selecting the right architecture for the specific problem and its constraints. So, power versus speed. Like I said, there's always been a tug of war there. This dynamic impacts every AI product you encounter as well. So the instant photo recognition on your phone, for instance, is optimized for power efficiency and likely runs on a custom designed chip. On the other hand, the lightning fast responses from advanced AI like ChatGPT or Claude or Manus, right, are powered by massive clusters of GPUs optimized for sheer speed. Understanding the balance between power and speed isn't just a technical trivia. It's the key to predicting which AI technologies will truly make it to market, which AI technologies will truly scale effectively, and ultimately, which technologies are going to change the world. So the next time you hear about an AI breakthrough, ask yourself, was this designed for the cloud or as an edge device? Is it primary goal training or inference? Is it built for maximum performance or long battery life? Answering these questions will reveal the real story behind the innovation and have you thinking more like an AI architect. Talk to you soon.